let's begin. Today's agenda is a key elements to consider of designing arena sound system. So we will discuss challenges, intelligibility and frequency, power and applications, controlling reverberation, sound delays, tuning the room of the facility, and examples of how to design arena sport complexes will be in the end. Type of sport complexes, it's like in general we discuss is hockey arenas, soccer fields, field houses, recreation facilities, gymnasiums, and aquatic centers. It's like major type of sports complexes. What the environment challenges we facing when you design the sound system for sport arenas? Surfaces hardness such as high ceiling, hard walls, and metal or wooden bleachers. All of these can cause acoustic reflections. Also, the size of arenas and weather, climate, environment, and sound treatment. So this will affect sound intelligibility, frequency response, sound delays, and etc. We'll discuss this next slides. So what the sound challenges of sport facilities? Is intelligibility and frequency response, power loudness, or audio coverage for entire facility, reverberant spaces, time delay for coverage, intelligibility, sound losses over the long distances, and controllability when you have globally or by zone. So let's discuss more deeply about the intelligibility. Measurement of intelligibility is called STIPA. It's acronym to Speech Transmission Index for Public Address System. It's measurement from 0 to 1. 0 is a lower index of intelligibility if it's very poor, and 1 is excellent. High intelligibility serves as a general mark of quality of sound. So it's very important for big arenas because higher distances and reverberant spaces create reflections, and sound waves can travel and bounce from different surfaces and create not good sound. So by using, for example, RTE meter, you can see here on the right side, you can measure this index. A sound system's frequency response refers to its basic tonality. A powerful, hard-throbbing bass comes from the low frequencies, and high-pitched sound effects come from the top. And intelligible speech is based on the combination of both, creating the full range of frequencies. So here, this small picture how affects sound waves and intelligibility. So if there is no interference of original sound source, it will be good intelligible sound. If there is some interference, noise, reverberation, the sound will arrive to the listener in a distorted way, so intelligibility will be poor. How to improve intelligibility? So to minimize the reflected sound and noise, in architecture, we'll usually adopt some kind of surfaces to absorb sound waves in the walls, in the ceiling, in other areas. Also using line array speakers to combat these issues is a high directionality of the sound waves. Also using a digital mixer processor to suppress reverberation and resonance. So by adjusting time delays and EQ, we can combat these issues with the intelligibility. Desired SPL. Listed below are typical sound pressure levels for various type of facilities. So it measures in an A-weighted mode, slow response. So as you can see here, we have different type of centers and complexes that require this average SPL value. So highest value is a large stadiums or arenas that have thousands of people, and higher SPL level is required. Power amplification. This section will suggest how big amplifier is needed for the value. Loudspeakers with the high sensitivity need less power than loudspeaker with low sensitivity. So it means that high sensitivity speakers, they're more efficient to convert electrical signal to the sound waves, and vice versa. Loudspeakers with low sensitivity, we need more power to push it the same SPL. So typical loudspeaker sensitivity is 85 dB per watt to 1 meter for home stereos, and 95 for PA speakers, 100, 105 for medium PA speakers, and for large PAs, 110. And here below, there is a term what the mean sensitivity. So you will measure sensitivity 1 meter from speaker and measure what the SPL level when you send 1 watt of power to that speaker. So this is the term of the sensitivity. The recommended power allows for signal peaks of 10 dB for music during events. And actually, sometimes it's even higher, up to 25 dB. So, but usually recommend to signal peaks up to 6 dB, and which music, like a rock, it's a heavy metal that is required for nice sounding of the system. And typical peak power or peak power is only 1 dB higher than continuous power and depends on the peak duration. So there's some examples for different type of arenas. With the small one, like 150 to 50 seats, it's at least 1,500 watts of power, total power of sound system. Music in a large stadium, like 100 to 300 feet from speaker to audience, it's 4,000 up to 15,000 watts. If there is a rock concert in arena, for instance, we're powered by 15,000 watts of sound system, and sometimes even more. So it depends what the size and what is the requirement. The sensitivity can be found in the speaker data sheet as well in TOA. TOA speakers is not exception. Typically, sensitivity for our speaker from 95 to 110 dB. Bigger speaker usually has higher sensitivity than smaller, but higher frequency drivers has a higher sensitivity than lower. So they use more power to drive than high power, high frequency speaker. And let's discuss about the peak headroom. So as we discussed, we need handle peaks from 6 to 25 dB above the average level, or other way is RMS level. The power amplifier needs to produce enough power to handle these peaks. So, for example, if speaker has an average power 100 watts or continuous power 100 watts, and desired SPL level should be achieved, we need to have up to 1,000 watts of power to handle 10 dB peaks. But it's in like ideal condition. In 6 dB, you can have 800 watts. It's good enough. And you need to use the compressor in the USB side to compress all these peaks to this level to not overload the speakers and amplifiers. Clearly, the peaks required for far more power than average level. So the calculator's peak headroom field enters 6 dB for rock music. This is compressed or limited to enter 20 or 25 dB for uncompressed live music. So meaning that if you want to leave it for 20 to 25 dB peaks to handle by sound system, you need to have this power amplification. How to control reverberation? A reverberant sound is a collection of all reflected sounds in facility like gymnasium. It's encountered in the larger facilities with the hard surfaces like gymnasium, large pools, etc. And sometimes this reverberant field is desirable for live music that will give you more depth sound. But usually for intelligibility, it's a this thing you need to combat with the sound treatment and DSP configuration. So bring the sound as directly to the audience as possible. This is one of the way to combat the reverberation. So bring the speaker closer to the audience. Also, line array speakers will have as well. So it will project the sound in a narrow angle and to cover longer distances. You need to be easy on bass. It's challenging to control the directivity at low frequency. So lower frequency will travel in omnidirectional way. So it's not directional. If you go into more higher frequency, medium and high, they are more directional. They are propagate in more directional way. So you can do some adjustment for the speaker. So bass, if it's loud bass, it creates more problems for intelligibility and reverberation. In certain spaces, treatments such as soundproofing, which acoustic panels, bass traps for lower frequency, and ceiling clouds will reduce the reflective sound. So if there is an indoor arena, like pool or ice rink, in the ceiling, we can place some ceiling clouds or panels will trap the sound and can reduce reverberation of the sound waves. So why is a line array work? So line array, it's a group of omnidirectional speakers, and they are arranged in the straight line. Also, each speaker can be adjusted. It's a can be adjusted by angle. Desirable angle depends on the size of the space. Closely spaced in the phase with the equal amplitude. So they are placed very close, and it's in phase with equal amplitude. So it's allowed to have more continuous, more flat waves with traveling. Again, useful for projecting sound over long distances, very directional, and more concentrated waveforms. And the longer the array, the more depth and low frequency control. Sound delays. Sound from the different speakers, far and close, will create problems with the sound delay. So what the meaning is, when both speakers start projecting the sound and they are in different distance to the listener, the sound front, the sound wave front will arrive to the listener in different time, and it will create bad sound because the sound waves in the different front will interfere to each other and will cancel or otherwise will increase. So it will create bad sound. So by delaying the output of near speakers, the sound arrives at the same time. So what does the meaning is you use DSP, for example, TOA M8080. You will delay near the speaker from the DSP, and when other speaker sound will arrive to this listener, it will arrive in the same time from the closer speaker. So the sound front will be in the same phase and in the same time they will arrive to the listener, and it will create more intelligible, more better sound. So how to adjust this delay time? By listening to the clicks in the area, delay measurement can be adjusted until this time right. So we can play some sound source that click sound, and by listening this click sound, we can adjust slowly delay. It's a millisecond to adjust in proper way that all both waves will arrive in the same time. Also, For more precise adjustment, you can use formula for sound delay that you will measure the distance from the nearest speaker and to the furthest speaker and delay and divide it by speed of sound. So you will know how much time the sound wave needed to arrive to the destination, to the listener. And by this time, you can put it in the DSP, and this will adjust the time delay to each channel. Final step in fine-tuning the system is equalizing speakers. So what do you mean? Each speaker has a frequency response that you can find in a data sheet. And usually the frequency response is not flat. Some frequencies above 0 dB, some frequencies below 0 dB. If you keep it flat EQ in the DSP, sound will not be great. You can make it better. How? And each DSP and TOA DSP as well has an EQ, parametric EQ. And you can adjust frequencies that it's like more high or more low. You make it more flat. So here there is example of red is some generic speaker that its frequency response is not good. Green line represent ideal frequency response that actually in the real world cannot be achieved. And yellow represents some kind of average of both and can be achieved by EQ. So it will create more better sound. Also, this frequency response is not only related to the frequency response of the speaker, but also the space. As we discussed before, reverberant space, surfaces create resonance frequencies that also affect this curve. So that's why you need to use equipment like RTA meter to adjust frequency on a DSP to make frequency response as flat as possible. Speaker consideration. The overall goal in the sports facilities is essentially the same, to deliver announcement and music to every spectator in the arena or stadium with a high degree of sound quality, balanced audio coverage, and clarity of speech. So what need to be considered? The amount of bass of low frequency energy needed and what type of subwoofer. And mounting of the speaker. So the location is also important. And also it depends on what the type of arena and the possibility to place the speaker. Challenges. Sound loses power over long distances, require high level of amplification and excellent pattern control to produce adequate volume to the stadium. So as you guys know, this inverse square law that double the distance, the sound pressure will reduce by 6 dB. It's quadrupled. So this should be considered when we design this system. So again, the size of the arena, the placement of the speaker, the audience sitting. So in our line, we have HX5 and HX7 linear speakers that you see below, and these speakers allow to adjust each portion of the speaker to achieve optimal performance and angle to cover near field and a longer field for sound suppression. So here's an example of line array and conventional speaker. So here you'll see this heat map that line array will more focus on the vertical axis and can project the sound in longer distance than conventional omnidirectional speaker. So again, conventional speaker will be omnidirectional. The sound waves will reflect from the roof and ceiling and arrive in different time to the listener and will create the bad sound. So that's why we have line array speaker that project the almost flat front of the sound wave and arrive to the listener not distorted. Design examples from TOA technical team. Let's review some few examples of projects. So this is hockey arena. There's a hockey ice rink and some rooms that need PA system, like fitness room, banquet hall, and maintenance. So we have head end. It consists of M864D and DPSP3. This is DSP with the faders, so we can lively change input and output gain. And DPSP3 is a speaker processor that allow you to easily adjust and fine tune the system. It has a preset for each speaker, so it will reduce the time and cost fine tuning the system. The speaker processor will connect to the amplifiers, the A500F and 250F. They both of them 4-channel. This 250 watt per channel, this 500 watt per channel. And they will be connected to line array speakers, HX5B, and subwoofer FB120B. They will be here in the middle of the ice rink. The next slide, I will show you how the sound pressure distributed. Also, as a source, we have wireless microphone system and MW41BT. It's a Bluetooth, USB, analog audio input that we can connect different kind of sources to play music and also connect the wireless microphone. Here we have we can see head end for PA system in these small rooms. It consists of M9000 M2. This is another type of DSP you have TOA has. This is a modular DSP, so you can select and insert these modules inside. And this D001R, it's an input module. D001K, it's output module. Can be up to 8 modules be inserted in this DSP. Also, we have paging mic connected to the input. We have amplifier and ceiling speaker in this area, and we have another amplifier and this ceiling speaker in this. So there are 2 paging for this area, and also this M9000. It's not showing here, can be connected to this DSP, and we can make paging for entire building, entire complex. It's needed. Here is a heat map of SPL levels on each zone. So this is ice rink. In the middle, you will see 2 left and right line array speakers, HX5B and FB120 subwoofers. They are projecting sound on the left and the right. This red area is more high pressure, and this more yellow and blue is on lower pressure than here in red. So you see the scale. So it's around 98 dB here, and from 90 in the corporate rooms. As well as fitness room and banquet hall has a ceiling type of speakers. They are placed well, and sound pressure and coverage is excellent. Another project I want to discuss is an aquatic center. So it has a large pool, small pool, lobby area, changing room, and current area. So large pool will have M8080, as you know, the DSP, wireless microphone system, and this device M800 ICTV is a touch panel allowed to do volume control, presets, and routing of the signal. You have few signals of music, or you have microphones, so you can do muting, you can do routing to the different outputs. The DSP will connected to these 2 DAs, and again to HX5B and FB120 line array and subwoofer. These rooms highlighted in yellow, it's a different zone. We'll cover with another M8080. We'll connect it to another DA amplifier, receiving speakers, and this is a volume control allowed to be almost the same as a list touch panel, but only the volume and source selection. Here, this zone will have pedal speakers and another type of ceiling speakers for paging. Smaller pool will have connection to the same DSP and will have another amplifier and another type of line array speakers. So this SR-S4L, it's a line array speaker. In order to combine these zones in one, this Dante has the option to insert Dante audio card. So Dante is a network protocol to sending audio to the network. So this will have network connection in between, and you can send and receive channels from each other and can do routing of the signal whatever you want, and what paging and BGM source to route to each individual zone. And here we have SPL coverage of the zone. So we see here on the side view, on the left and right side, two line array speakers. We project it down. This will not create any problems because the water here works as a sound absorption, and it will not create any unnecessary or unwanted effects, sound waves like a combing effect or reverberation or any other things. Thank you for listening.